This is part one in a two-part series about kinetics. And today we're going to talk about kinetics. Kinetics is all about reaction rates, how fast things move, how fast concentrations appear, how fast concentrations go away, and you're very familiar with kinetics in your life. You're familiar in terms of meters per second, centimeters per year when you talk about a glacier moving. Snails, my goodness, how fast do they move? But there's still a rate. Windmills turn, trains move, paraplegic athletes move around a course, or they run or race using their wheelchair. So you're used to a rate of change. And so if you look, and it's per unit time, if you look, what rate is sorry, come on. Rate is the change in something, so it's the change in miles per the change in time. You're used to miles per hour. But in terms of what we're talking about in chemistry, we're talking about rate equals the change in concentration of something. We're going to call that A over the change in time. And if you look at what this delta means, this change, how do you calculate that? Well, we've always taken whatever we've ended up with and subtracted what we started with. You think about that when you have a stopwatch, you actually have time 0 and then you click it and then it continues on and you stop it. So your stopwatch takes the final minus the initial and gives you a positive value for time. So to do this, we're going to take whatever the concentration of A is, final, minus the change in not the change, but the concentration of A at a starting point, or initial. So final minus initial, or concentration at time 2 minus concentration at time 1. So we're going to go ahead and do time the same way. Time final minus time initial. So if you look at this equation, it's this version just written out and explaining what that delta means. So let's put this to use. So when we're doing this, we're finding the rate, a rate. And that rate again is change in concentration of something. Again, we call it A over change in time. And that gives us a rate. So let's look at this experiment. And sorry, my 600 down here kind of got moved over and I can't shift it. So this SO2Cl2, again, which is supposed to be subscripted like this, and it didn't turn out, it is reacting. It's a reactant, and SO2, sulfur dioxide, and chlorine are produced. So I think you would agree with me at this point in time that this is a reactant and these are the products. Correct? So I'm going to go ahead and highlight these. Oh, that's not highlighting. So these are the products. This isn't working, is it? So these are the products. There you go. And this is a reactant. In this case, there's only one reactant. And so if you look, this is what's happening. At time 0, we have 0.100 molarity. That many moles per liter. It's a concentration. And as time ticks away, our experiment occurs, less and less SO2Cl2 is present. And you can see that because as time goes along, the concentration is decreasing. Makes sense, doesn't it? Because what's happening is a reaction occurs. The reactants go down because they're producing more products. So what we're going to do is we're going to find the rate. And to do that, I need to actually do this, change in concentration over change in time. So I'm going to go ahead and just pick 2 random times. I'm going to pick 600 since it's indented for us here. Okay, seconds, that's how this top happens to be in. and 100. So to do a change in concentration, I'm going to find the rate. This is my final, this is my initial, and I want to know how fast SO2Cl2 is going away between 100 seconds and 600 seconds. So to do that, let's do time, that's easy. 600, my final, seconds, minus 100 seconds. All right, now let's look at our concentration. At this 600 second mark, I have 0.030 molarity, right? That's what this is, molarity, moles per liter, minus 0.100 molarity. That's change in concentration of A over change in time. If you do your math, you end up with negative 0.52 molarity over 500 seconds. And so our actual rate is negative 1.04 times 10 to the negative fourth. And our units for that are molarity, or moles per liter, per second. Which means that as every second goes by between this 100 to 600 second time period, it is disappearing at a rate of 1.04 times 10 to the negative fourth molarity per second. And you know it's disappearing, okay? This is a rate of disappearance. Why do we know it's disappearing? Well, number one, it's a reactant, so it's going away. But that's what this negative means. That negative means it's disappearing at a rate of 1.04 times 10 to the negative fourth meters per second. If that bothers you, then simply just take that negative out. When it appears up here, okay, it's a negative right there. What's that mean? That means, whoops, it's disappearing. Okay, it's going away. So simply, it's just change in concentration over change in A to find a rate, or the rate of a reaction. You can look at graphs. Now this graph is not the equation we were just looking at, but you can look at a graph and you can see where the reactants are and where the products are. So let's look and see if we can determine that from what's going on here. Make sure I have the right color markers. And if you look, we have a blue line and a red line. Our x-axis is time, and our y-axis is concentration. And we control time, that's our independent variable. And as time goes by, right, it's going from 0 to lots. And this is going from 0 to lots or more. How do you know which one of these is a reactant and which one's a product? Well, at time 0, on this blue line right here, let me change markers. On this blue line right here, you have basically nothing. And on this red line, you have some. So that means that your reactants are H2 and I2, hydrogen and iodine. Chances are these are a gas. And you know that you have these, okay? And in this case, hydrogen and iodine are the same amount, and they're also disappearing at the same amount based on this red line. How do you know that HI is produced, hydrogen iodide? Well, because at time 0, you have nothing. And as time goes by along this line, more and more of this blue line, more the HI is produced. And as time goes by, this hydrogen and iodine decrease. So these are going down and this is going up. Now there's a ratio here. First of all, this is not a balanced equation, so let's balance it. I'm going to put a 2 out here. Okay, I'm going to go back and erase these lines here. Okay. Now if you look, what are these variables? If I find the rate, how do I do that? What was the equation again? Oops. change in concentration, in this case of H2 or H2 or iodine, right? These are going away. So this is my y-axis, isn't it? And what's my x-axis? That's time. So if you look, this dotted line right here, this is my rise, my y-axis, and this is my run, my x-axis. What do we call that? Slope. So slope shows rate, doesn't it? If you look it up here, what's happening? You have a rise and you have a run. And the slopes are different. In this case, it's a negative slope because hydrogen and iodine are disappearing. They're being used up. And in this case, it's a positive slope because hydrogen iodide is being produced. So there's some graphical evidence for you. All right? Now, I'm going to go ahead and use this page for a second to show you something different. Let's go ahead and clear all this junk. I'm going to go rewrite my equation. And if you look at this for a second, I can tell you what's going on. If you look back here, we found a rate, right? What was this rate? It was the rate of how fast SO2-Cl2 was disappearing. And we can measure that because if you have a reactant in a beaker and it's being used up, it's reacting, it goes away. We know how much we started with. Okay, let me get rid of some of this stuff too. Okay, we know how much we started with. We know it's going down. And we know how much we end with, which is going to be less. At this point, we're not really ending, but we're stopping this reaction at 800 seconds. So you can see very clearly it's going down. So as these are going down, what's happening to both of these reactants? They're both going up. And they're going away and being produced along with the molar ratio. For every 1 mole of these goes away, 1 mole and 1 mole of these are produced. So let's go over here for a second. And let's just say that I know that H2 is going away at a rate of 2.6 times 10 to the -4th molarity, and it's negative. Okay, and I just made that up. Just pulled it out of the blue. And I know that this is the rate of disappearance for H2. And if I had figured that out, I would have figured it out using that rate equation. Rate equals change in concentration over change in time. And I can do that graphically, or I can do it using information in a chart like this. So now I would like to find out what my rate of appearance is of hydrogen iodide. How fast is hydrogen iodide appearing? So the rate of appearance, you'd have to figure out using the rate of disappearance for H2. So if I know the rate of disappearance for H2 is -2.6 times 10 to the -4th molarity, oops, and this should not be just molarity, it should be molarity per second, or per minute, or, okay? So go back here. This is my rate of disappearance. Now I'm going to do myself a favor, and I'm going to get rid of this negative out front. And why was that negative there again? Because it showed you that it was going away. So if H2, I'm just having pen difficulties today, sorry. So if H2 is going away at a rate of 2.6 molarity per second, this is hydrogen, how fast is hydrogen iodide being made? You're going to use stoichiometry to do this. You do not want moles of hydrogen. You do want moles of HI. And I got 1 from the balanced equation up front here. and I should have 2 here. Do you agree with me that for every one of these that goes away, moles, the 2 of these are produced? Yes, indeed, you do. And because molarity is moles per liter, I'm going to go ahead and use a stoichiometric ratio of this 1 to 2 and put it here. And look what happens. My moles of hydrogen go away. Not moles, not the liters, but the moles do. Right? That cancels out. That moles is then again substituted back in. My hydrogen goes away and I'm left with hydrogen iodide. So if you look, get rid of this mess, what happens? I have, goodness. All right. I have a rate of disappearance and a rate of appearance, and would you agree with me that this is appearing twice as fast as this is going away? Indeed it is. And so if you look, that's exactly what the math says. So what do? You take 2.6 times 10 to the negative 4th, and you multiply it by 2. And that means that this is being produced at a rate of 5.2 times 10 to the negative 4th molarity every second. In other words, if this is disappearing at a rate of 2.6 times 10 to the negative 4th molarity per second, then hydrogen iodide is appearing twice as fast. So you could use words to express this, describe this. You could say, since hydrogen gas, probably gas, is disappearing at a rate of 2.6 times 10 to the negative 4th molarity per second, and the molar ratio between hydrogen and hydrogen iodide is a 1 to 2 ratio, then hydrogen iodide is appearing twice as fast as hydrogen is disappearing. Therefore, hydrogen iodide appears as a rate of 5.2 times 10 to the negative 4th molarity per second. Or he can just do the math. I like the math. So let me go back through this math again real quick. Okay? And I could tell you how fast iodine is disappearing. How fast is iodine disappearing? Well, if you look, there's a 1-to-1 relationship, isn't there? So hydrogen is disappearing at the same rate as iodine. They're the same. You can see that graphically also, can't you? They're the same. So how do we do this again? Let's make up a different number. Okay? Let's say, in this equation, that I know the rate of disappearance of NO2, it's disappearing at a rate of 2.6 times 10 to the, I keep picking 2.6, don't I? 2.6 times 10 to the negative 3 molarity per minute. Okay, now why is that negative there? That negative is there because it means it's disappearing. How did I figure that out? I got to figure it out by looking at a graph or looking at a chart. So if it's disappearing, I'm going to go ahead and get rid of this negative. What do I know? I know in my equation here, my balanced equation, that for every 2 of these, I make 2 of these. And for every 2 of this reactant, I make 1. So I want to find out the rate of appearance of oxygen when nitrogen dioxide is disappearing at a rate of 2.6 times 10 to the negative 3 molarity per minute. This is NO2. And so I'm going to put, for every 2 moles of NO2 that goes away, 1 mole of oxygen is being produced. And if I do my math, I'm going to go ahead and take 2.6 times 10 to the negative 3 divided by 2. And that equals 0.0013 molarity per minute. That's the rate of appearance of oxygen. Moving on. Now, we have rate, but I have something else called a rate law. And that rate law means I would like to know a little bit more about my reactants. How reactive are they? Are they reactive like a birthday candle, or are they reactive like nitroglycerin or dynamite? What do they do when they hit my liver, my kidneys, my lungs? How fast does a reaction occur in my battery in my car? So to do that, we can't use this equation. Through math, mathematical manipulation, calculus, I'm going to go ahead and come up with what's called a differential rate law. Right? Now I'm not going to show you how this is derived, but this is called a differential rate law. And a differential rate law, look at this, here's rate. So here's rate and here's rate. This is called a rate, and this is going to be called a rate law. A rate just measures the change in concentration over change in time. A rate law actually gives me information about what happens if I change a certain reactant. What's it going to do to the rate? All right, so rate is equal to K, which is called the rate constant. And I know I'm misspelling it, but I'm doing it on purpose because baby K goes with kinetics. Capital K goes with equilibrium, right? Remember that? So this is baby K, and that's equal to not the change, sorry. It's equal to the concentration of A to a power. That power is going to be a number. So this is rate law. Let's go ahead and learn how to do rate law problems, and you can see what they look like. They're completely different than finding the rate. Rate law, you have a completely different chart. You still have a balanced equation, and in this case you have two reactants. All right, and so these two reactants, OCl minus ion, the OCl minus ion and the iodine ion, here they are, right here. Here's your molarity per liter per second. They have a molarity per second. Those are the concentrations.